So now we know how to pick a quadrant, kind of isolate our quadrant. Now we're actually gonna get to a number, an actual axis number. That's going to take a couple extra steps. So we talked about this big broad quadrant. Now we're going to kind of hone in a little bit. So we found the quadrant. Now we're going to find an isoelectric lead. We're going to kind of hone in on that closest lead, and then we're going to narrow it in. We're going to double check our findings. So first, what is the isoelectric lead? We've got our quadrant. So our next step, our second step, we're going to look at our 6 limb leads. Lead 1, 2, 3, AVF, AVL, AVR, or AVR, AVL, AVF. We're going top to bottom. Look at our 6 limb leads and which one of those limb leads has the smallest amplitude, smallest voltage. Which of those leads is like the smallest, cutest little eensy beensy lead, and that's the one we're going to pick. Maybe, sometimes, kind of, sort of, maybe. You've got 2 leads that are about the same amplitude, top to bottom. They're both really small. We're just going to pick the one that's kind of like the most isoelectric, the most balanced between positive and negative. So when picking this lead, we're looking at these 6 limb leads and we're saying which one is the smallest in amplitude, top to bottom. So let's put this into practice. Let's look at example 1. So step 1, we're going to pick our quadrant. Lead 1 is upright. AVF is upright, even though it's a little bit of negativity to it, right? It's mostly upright, or a little bit more upright than it is negative. We picked our normal axis quadrant because we're upright and upright. We're positive and positive. But now we're going to pick our isoelectric lead. That's step 2. So which one of these 6 leads has the smallest voltage, smallest amplitude? And you know what? Lead 3 and AVF, they both look pretty small, top to bottom. QRS, that is the QRS amplitude. They both look pretty small, but lead 2 is completely negative. AVF has some positivity and negativity to it, so we're going to pick AVF as our isoelectric lead. And here, what we're going to do is take our hexaxial diagram. We've already picked our quadrant, but we're going to draw this like thick line, and here we have a thick blue line straight through AVF. We'll talk about this red arrow here in a few minutes, but for the time being, we've got this thick blue line through AVF. We know we're going to be in the normal quadrant or thereabouts, but AVF is my isoelectric lead because it has the smallest, little tiniest voltage. It's so cute, right? And we've got this. We're just going to draw a line straight through AVF. In example 2, we've got lead 1 is negative, AVF is positive. We picked our right axis deviation quadrant right down here because 1 is negative, AVF is positive. And then we look and say, well, which one of these complexes is the smallest in amplitude, top to bottom? And that looks to be AVR. So we're going to draw this really thick line. We're going to draw a line through AVR. So now AVR is my isoelectric lead. In example 3, lead 1, positive, AVF, negative. And that puts us in our left axis deviation quadrant. Lead 1 is positive, AVF is negative, and we look and see, well, which one of these is the smallest in amplitude? And again, get your calipers out because lead 2 looks kind of small, AVR looks kind of small. AVR is going to be the smaller of the two, top to bottom. So AVR is going to be our isoelectric lead. I draw a big old thick line right down AVR on our hexaxial diagram. So now we've found the quadrant, we've found our isoelectric lead. Now we're going to start to kind of narrow in, kind of hone in. So step 3, we're going to find that closest lead, the closest in quotation marks. So what we're going to do, finding this closest lead, this is when that arrow comes in. So we're going to take our isoelectric lead and we're going to use kind of this T-bar. So we're going to draw an arrow completely perpendicular to our isoelectric lead line, and that's going to get us within 30 degrees of our actual axis. So we've got our isoelectric lead, we drew that big thick blue line that you saw, And from there, we're going to shoot out this red arrow at a perpendicular, like a 90-degree perpendicular um, angle to get us kind of close-ish to our final degree number. In example 1, we were in the normal axis quadrant because we are upright in lead 1, and we are mostly upright in AVF, so positive and positive puts us in the normal one. We picked AVF as our isoelectric lead, so here's our big thick line. Now I get to point my arrow, my red arrow, and I'm pointing it to the right. I could point it to the left, right? I could go in either direction, but I'm going to the right. So why am I doing that? Why are we doing that? Well, because that's the one that points towards ish the normal quadrant. If I were to point it to the left, that would put me in the right or the extreme right area. And that is completely opposite of the quadrant that I picked. So we're always going to point that arrow, we're always going to have two options of where to point that arrow, and we're going to point it in the direction of the quadrant that we picked. So we picked the normal quadrant because 1 is up. AVF is mostly up, mostly positive. So we're going to point it in this direction. So as I'm starting to get kind of honed into a number, AVF is my isoelectric lead. I've got my arrow pointed at 0 degrees. We're going to kind of adjust that a little bit here in a few minutes, but that's where we're gonna end up. In example 2, we ended up in our right axis deviation quadrant. Lead 1 is down, mostly negative. Lead AVF is upright, mostly positive, so we are in the right axis deviation quadrant. We picked AVR as our isoelectric lead, and there's our big thick blue line. And then I'm going to draw that 90-degree, that perpendicular arrow in one direction or the other. So I can go down or I can go up, and I'm going down again because we picked that right axis quadrant. If we had picked the left axis quadrant, then I'd be going up. I'd be pointing in that direction. But it doesn't make sense to go in the opposite direction of the quadrant that we've already picked in our first step. So I'm pointing down into our right axis quadrant area. I'm ending up at positive 120 degrees. And again, we're gonna adjust that a little bit here in a few minutes, but that's where we're gonna end up at the moment, at the end of this step, and at the end of step 3. For example 3, we are in the left axis quadrant area. Lead 1 is upright. AVF is negative. We are in the left axis quadrant. We picked AVR as our isoelectric lead, the smallest in voltage and amplitude, top to bottom, for the QRS complex. So here's my big thick blue line here on AVR, and then I'm going to point my arrow at a perpendicular angle, either up or down. And again, here I'm going up. Example 2, I went down because we picked the right axis quadrant. But in example 3, same isoelectric lead, but I'm going up because we picked the left axis deviation quadrant. So I'm going up. Again, this is at a perpendicular angle, so we end up at negative 60 degrees, and then we're ready to kind of to play a little bit. So now let's narrow in our vector a little bit, right? So we found the big broad quadrant, big and broad. We found the quadrant. We found our isoelectric lead. We found that closest lead. We've got that big thick blue line. We drew our arrow at a perpendicular angle. We've got a number. Maybe it's 0 degrees, maybe it's negative 60 degrees, maybe it's positive 120 degrees, but we've got this number. Now we're going to narrow it in a little bit. So it's not exactly 0. Oh, it might be exactly 0, but it's probably not exactly 0. It's probably not exactly negative 60 degrees. So we're going to adjust a little bit. Now, how do we adjust? Well, we're going to go back to step 2. We're going to look at that isoelectric lead. That teeny tiny little small amplitude lead. We're going to look back at that and say, well, okay, is it more positive or is it more negative? And if it's more positive, we're going to shift our arrow a little bit in a positive direction. If it's more negative, we're going to shift our arrow a little bit in a negative direction. And we're going to shift it by 10 degrees or 20 degrees. And that's going to be based on if it's like super positive or super negative. So if it's like all positive or mostly positive, we're going to go a positive 20 degrees. If it's like just a little bit positive, okay, just a little bit, and then we can go 10 degrees positive. Same thing with the negativity, it's like super negative. We're going to go negative 20 degrees. And it's just like a little bit negative, just a little bit. It's going to be a negative 10-degree adjustment. So a little bit of subjectivity here based on your interpretation of it. You know, should it be a big adjustment, a 20-degree adjustment, positive or negative, or should it be a small adjustment, a negative or positive 10-degree adjustment? And we're taking this isoelectric lead, that one lead that you took out and said that's like the teeny tiniest, cutest little complex that I've ever seen on this EKG, and that thick blue line that you chose is that lead, and you're looking at deflection based from base from baseline, deflection from the baseline. Is it more positive? Is it more negative? If it's more positive, is it like a lot more positive? If it's more negative, is it a lot more negative? And that's going to determine this 20-degree positive or negative adjustment or this 10-degree positive or negative adjustment. So if it's a lot, we go 20 degrees. If it's a little bit, we go 10 degrees. For you visual learners, here you go, right? So this is my isoelectric lead, whatever lead I picked. It's a lot more positive, I'm going 20 degrees. It's a little bit more positive, I'm going 10 degrees. It's a little bit more negative, negative 10 degrees. It's a lot more negative, negative 20 degrees. If it's completely isoelectric, if it's completely like equal, equiphasic, positivity and negativity are the same, bam, you're done. You don't have to adjust it if it doesn't bear adjusting. So if it's completely equiphasic, no adjustment needed. But if it's a little bit more positive, a positive 10 degrees. If it's a lot more positive, a positive 20 degrees. If it's a little bit more negative, negative 10 degrees. If it's a lot more negative, then a negative 20 degree adjustment is needed. Now here's the wrench I'm going to throw in everything, because I know you're like super stoked about this. You totally know what's going on, and I'm just gonna throw a bucket of bolts in your engine here. So, in this example, and this is just a generic example, we picked AVL as our isoelectric limb lead. We drew our like thick blue line through that, and in this example, we're in the normal axis quadrant. So we drew this perpendicular line, arrow, and we ended up at 60 degrees, a positive 60 degrees. That's great. Now we're going to do an adjustment. And in this example, we're doing a positive 20-degree adjustment. I'm going to repeat that. We're doing a positive 20-degree adjustment. And with that, the arrow moves this way, up here. And we get to a final axis number of positive 40 degrees. So, wait a minute. Hold on. I totally took Math 101. I took algebra. I took calculus. I know this. I did a positive adjustment. We started at 60. I did a positive 20. Why am I not at 80? Why am I at 40? That doesn't make sense. Wait a minute. What? Okay, so what we're doing. Every lead has a positive and a negative pole. So AVL, this is the positive pole. When I do a positive adjustment, I'm going to move towards that lead, towards that positive pole. If I were doing a negative adjustment, I would move away from it. whatever lead it is. If it's AVR, lead 1, AVF, lead 3, whatever it is. If I'm doing a positive adjustment, I'm moving towards the lead. If I'm doing a negative adjustment, I'm going away from the lead. So please do not get in the habit of just adding and subtracting numbers when we talk about positive and negative adjustments. Sometimes it'll work out for you, and sometimes it won't. In this example, it would not work out for you. So we did a positive adjustment, and we started at 60 degrees, and we ended at 40 degrees, and that's a positive adjustment, not a negative adjustment, right? Because we're going towards the lead that we chose. We're going towards that positive pole. So just don't add and subtract. Please, please, please pay attention to where your isoelectric lead is, and a positive adjustment goes towards it. Positively. I like you. I positively like you. So we're going towards you. Negative adjustment, I don't like you. Screw you. I'm going away from you. So if we did a negative adjustment, then we'd end up at 80 degrees. But a positive adjustment, we ended up at 40 degrees. Let's go back to example 1. We were in our normal quadrant, normal axis quadrant. Lead 1 is up, AVF is mostly upright. We picked AVF as our isoelectric lead. Because we're in the normal quadrant, we pointed our arrow to the right and not to the left, because that would put us in the right, extreme right area. Nope, we want to point towards normal. So we're pointing towards normal, pointing towards our quadrant. We end up at 0 degrees. Then we look at our isoelectric lead, AVF, and it's just like a little bit more positive, right? Because we said it was a little bit more positive when we picked our quadrant. So it's more positive, it's just a little bit more positive. So it is a 10-degree adjustment. So we started at 0. We're going to move towards our isoelectric lead. We're going to move towards AVF. So we're going from 0 to 10. So we end up at an axis of positive 10 degrees for this 12 lead. In example number 2, we picked our right axis deviation quadrant. Lead 1 is negative, AVF is positive. We're in the right axis quadrant. We picked AVR as our isoelectric lead, so big thick blue line through AVR, and our perpendicular arrow down to the right. All right, we could go up, then we go into the left quadrant. That doesn't make sense because we already picked the right quadrant, right axis deviation quadrant. So we're going to go down into that quadrant. We end up at a positive 120 degrees. And then we look back to AVR. Is it more positive? Is it more negative? It is more positive, but in comparison, it's just a little bit more positive. It's not like a ton more positive, it's just like a little bit more positive. So we're going to do a 10-degree positive adjustment. So we're going to go towards AVR, towards our isoelectric lead. So we go from 120 to a positive 130-degree axis number. And then in example number 2, we're in our left axis quadrant here. So lead 1 is up, AVF is down, is negative. We're in our left quadrant. We picked AVR again as our isoelectric lead. Here's our big thick blue line. We drew this perpendicular arrow up and into the left quadrant. We're not going to draw it into the right quadrant, because that doesn't make sense. We already picked our left quadrant, so we're going to draw it into our left quadrant. We end up at negative 60 degrees. We look at AVR, and is that more positive, more negative? It is definitely more negative. It's a little bit, there's a lot. It's a lot more negative. It's like all negative. Look at that thing. There's no positivity to it. It's all negative, so we're going to do a negative 20-degree adjustment. So we've got AVR here. We're going to do a negative adjustment. We're going to go away from AVR, away from our lead. Again, don't add, don't subtract. We're going away, towards or away. Here, a negative adjustment, we're going away. So 60, we're going away 20 degrees, and we end up at a negative 40-degree axis for this 12 lead.